Well, I suppose we have a few minutes to go, but just in a general sense, I guess, talking about this class, as you know, from if you saw the email from yesterday, this is week 10 for all of your classes. I think we have, not I think, but I know we have 4 weeks, including this one, until Thanksgiving, and then 2 weeks afterwards. Is that right? Yeah, so 10, 11, 12, 13, 14, 15. So six weeks of classes. So before Thanksgiving, I guess we'll have 3 weeks of classes. So we'll talk about pipe flows for the next 2 weeks, starting today. And we'll talk about external flows, flows around wings, flight structures, drag on cars, etc. For 1 week. So that'll be 3 weeks. And then it's the presentations for the immediate week before Thanksgiving. And so I'm not sure how you're planning on doing that. A growing number of people last year just posted them on YouTube and didn't come to class and do them. I think that's still fine this year. So I'm not sure what people will do. But regardless, there will be sessions that week on the Monday, Wednesday, Friday in class. Depending on how many people opt to do it online, I guess we'd have to also make some evening sessions as well. So it just depends what people will end up doing. I'm just having that play in the background. I guess we have 328 students in this class. So groups of 5 means we have 60 groups. In one class period we have 50 minutes. So that's 10 5-minute presentations. So 60 presentations will take 6 periods, and we have 3 periods to do it. So depending on if half the class decide to do it online, then we'll just do it in class, and that'll be fine. If not, we'll have to make an evening event of it as well. So that's so 4 weeks until Thanksgiving. You get Thanksgiving off, of course, and then 2 weeks back after that. And so in the 2 weeks back after that, we'll talk about open channel flows, and probably we'll talk about open channel flows for 1 week, and then we'll use the final week, just the 3 periods, to review stuff through the class. There's one more midterm. The final is nominally comprehensive, and that's why we'll go through everything in the class, but in practicality the final has always been weighted on the stuff in the last quarter of the class, and I think that's probably going to be the case this week as well, this year as well. So just so you know where you are in the big picture. So that's where we are. So as we said before, great to have you here in the morning. Remember, it's a marathon, not a sprint, and so we're getting through to hopefully to the finish line slowly but surely in this, and so those are the things we have remaining. So you should be able to get 100% on the presentations, or close to, if you're putting effort into it. There is a peer review system, so that if someone isn't quite pulling their weight, then you can comment on that, and that'll be taken into account in the grades. Usually it hasn't been an issue. I guess I only remember one time when the presentation, there were 5 people presenting, and 4 people presented, but one person wasn't allowed to present and was standing up there anyway, and no one was talking to them, and they had a little Facebook spat over what was going on, and we sorted that out. But that's been the exception rather than the rule, I think, in all of this. So yeah, so that's where we are with this. Thanks for coming. I don't know whether at some stage this class should migrate to all online. Actually, I'd be kind of curious as to what your thoughts were on that. Why did you guys come? Do you have a class immediately after this? Lots of heads are nodding. So what is that, Brownson's class or Radovic? Radovic, yeah. So, good. Glad you're here for that. Yeah. No, I'd actually be interested to chat with people sometime. I do have an open door policy, and it's good to drop by in an afternoon and just introduce yourself. I think that's probably an interesting thing to do in your careers anyway, not just with me, but with anybody, just because making some connection with faculty here. These faculty might be people who are writing you letters of recommendation, not from a big class necessarily like this, but from some of your intimate classes. Good to be able to have a conversation with an adult and be able to get yourself known in some way, because you might need a letter of recommendation for grad school or for job purposes. So that's just a life advice. Okay? All right, so what I wanted to do today was maybe to recap material for the last couple of weeks, just to say exactly where that fits into the grand scheme of things. There are 2 very specific things that you've been doing, and as we talk today, we'll talk about pipe flow, which is obviously what's going on in the background here, that if you look at flow along this pipe, then initially, the flow at some velocity is laminar. It's sheets of flow which are sliding next to each other. In the center of the pipe, it's uniform. And then as you increase the velocity and also get further downstream, you get these little wiggles in it. And so this is, in this case, it's because the velocity is being increased and the flow is going from laminar in the initial circumstance to a higher velocity and therefore a higher Reynolds number, at which case it transitions from one flow regime to another. And so that's what we'll be talking about. And actually we'll be using the information that you've gathered over the last 2 weeks to be able to talk about this. And the information on the last 2 weeks, I think, has been two particular areas. Actually, I'm just going to draw. And the two particular areas are energy equation, which has been a modification, if you like, of Bernoulli, and also of dimensional analysis. And so we'll use both of those concepts today when we start to talk about flow in pipes to be able to develop some expressions that allow us to be able to solve for what power you have to put into a pipe network to be able to get a fluid from the Gulf, gas in the Gulf, to someone's kitchen in New York City. What kind of energy do you have to put into the system to be able to do that? So let's talk a little bit of this. So we are week 10. This is pipe flows. But first I just wanted to recapitulate, I guess, which is what recap is short for, on the two things that we talked about. The first is the big picture, so the energy equation. Comes in a variety of forms, but the one that we'll use most usefully, I think, is to go from upstream to downstream. And of course, actually the pipe network could be all kinds of things in it, with a pump in it, to go from upstream to downstream. By convention, I don't know why I always have flows going from left to right, but I do. And the idea is simply this. We talked about this concept before. And that is that if you look at a length in the x direction, you could imagine that at this point here, then there is a portion of the pipe which is an elevation, a portion of the pipe which is a pressure head at 0.1 over unit weight, a portion of the pipe which is a velocity squared, v1 squared over 2g term. We know that all of these terms in themselves are units of length, and so this constitutes Bernoulli's expression. We talked about the fact that we could have an energy grade line, which is something that is constant, just a constant magnitude. And so now if we come over to this downstream point, clearly the elevation will be the same magnitude, Z2. The pressure may be a different magnitude, presumably it is if it's flowing from left to right, P2 over gamma. And we know that if the pipe is the same section, so if we know that V1 A1 is equal to V2 A2, if we know that both of these cross-sectional areas are the same, then we know that both of these velocities have to be the same. And if that's the case, then this height of this velocity has to be this, V2 squared over 2g. And so this length and this length have to be the same. This height and this height have to be the same. But if we're flowing stuff, pushing it downstream, we're losing pressure as we go from upstream to downstream. And so this P2, I guess, would be less than P1. And so the missing component in this is what we've called the loss. So that's kind of the graphical view of this. And so if we write Bernoulli's equation in the way that we now know it, upstream elevation, upstream pressure, upstream velocity. We can put some energy into the system in a pump. The units of this have to be head, just like all these other terms as well. And if we look downstream, then it's just the continuation of this, P2 over gamma W plus V2 squared, 2G, plus the sum of head losses. And so the graphical explanation of these are frictional losses. So these are what we'll refer to as viscous losses. That's why people put friction reducer in well bores, so that the pumping that you apply at the top of the well bore when you're doing a hydrofracturing job is manifest at the bottom of the hole, instead of all being eaten up in physically moving that fluid at relatively high velocities along the downstream portion of the pipe. And so if you can reduce the friction, reduce the viscosity, then you get much more pressure downhole, and therefore much more bang for the buck in some respects. But that's physically what it means. And we won't talk about what HP will do in here. I guess it would change the form of this grade line, but let's not worry about that. So that's the first thing that is relevant to what we've done. So we've solved for energy, and now for the first time, instead of dealing with Bernoulli's equation, which is inviscid, so you remember that Bernoulli is inviscid. In other words, the viscosity is 0. By adding this term, we can allow the fact that viscosity is no longer equal to 0. And so we've got to figure out exactly how to use that. So that's one thing that has come out of maybe the week 8. It's really the key message from this is that we can define exactly what those. We'd like to be able to figure out what these viscous losses are. So for instance, if you're pushing stuff from the Gulf to New York City, this might be something you'd like to be able to figure out, because if you know what this is, then you can calculate how much energy you have to supply to be able to move it upstream. So that's the first part in dealing with this. The other thing that we did, which I guess moves into talking about dimensional analysis, so this is week 8. This is week 9. And of course, dimensional analysis is this incredibly powerful method by which, if this works, this is one of the movies that maybe you looked at. Will it refresh? Is that you can put a structure, so you don't need to solve any equations to figure out exactly what the forces might be on a structure. But what you could do is you could do an experiment by towing a ship in a tank, putting an airplane in a wind tunnel, and being able to measure some forces in it. So in this case, maybe with the air flowing past it, there are two things that we'd be interested in. The first is that the flow patterns around the wings, we'd like to have the same flow patterns around the wings in this wind tunnel as happen in real life. And so there's something called kinematic similitude that we want to guarantee. Exactly the same flow patterns around them. And if that's the case, then what we could do is we could measure the forces that are applied on this plane, either in lift or in drag, pushing it down the tunnel, and be able to scale those up to the fact of a full scale. I don't know what scale this model is, or whether it's actually a full scale plane. We could use it to be able to scale what the forces would be in reality applied to this. And so we don't need to solve any expressions to be able to do that. We can just use this quite incredibly powerful technique called dimensional analysis. And I don't know if you can hark back that far in our past, but the very first time we met, actually the second time we met, I think on the first Wednesday, we talked about using Bernoulli's equation, and we talked about taking some of the individual components of that, right? We talked about maybe taking, I'm going to go down here, taking these two components, and I'm going to mark one of them to put it on the top. So if we take these two and we divide this one by this one, what do we get? We get P over rho G. Units of length, if we divide by units of length, the term has to be unitless, and that we're talking about homogeneous units in our equations. And if we divide by v squared over 2g, right, just taking these two terms, and what do we have? We end up with getting rid of this, we end up getting this, we end up with P over rho v squared. And if you looked at the material from last week, then you know that that's referred to as the Euler number. And so we know that if we have a magnitude of a flow velocity and a density of a fluid that's flowing over something, we can calculate what the pressure would be applied to that building, applied to that airplane, applied to that wing in lift, and we should be able to calculate exactly what that is without doing any kind of solution of equations. It turns out that the equations that we solve, we aren't very good at doing that. So typically we solve linear equations, but fluids are often non-linear. Viscosity doesn't vary linearly because we get turbulent flows, etc. But these relationships from dimensional analysis apply irrespective of the constitutive laws that we have for these fluids. So that's one thing. The other term that we also dealt with, which I want to deal with here, which is this. So this is the, and you remember also, what was this? Right? You remember that this is also this division of Bernoulli's equation. Solving F equals ma, this is the inertial term. If you destroy momentum, rate of change of momentum is inertia. If you destroy momentum, then you have to apply force as a result of that. Get hit in the chest with the gas, the wash out of a jet engine. It kills the velocity on your chest. In killing this velocity, it exerts a force on you. And so the other expression that we dealt with, where we take this term here as the numerator. So if you take v squared over 2g, a unit of length, and if we divide by z1, 1 over z, what do we end up with? We have, ignoring the fact there's a factor of 2 in there, we end up with v squared over gz. And if we take square roots of both sides, which we can, which is equal to v over square root gz. And if you have remembered from what you talked about last week, this is called the Froude number, which we call F sub r. This is the Euler number after the Swiss engineer, mathematician, who actually I think used to appear on the one engineer that might have appeared on a note, a Swiss franc note. And so these are terms that are important to us. Froude numbers are important where the flow is driven by gravity, and we'll talk about that later. And so the Euler number is where we're interested in flow either around an object or through a pipe, for instance. This is where there's a free surface in it. If you're towing a boat in a flow tank and the gravity is the only real force that's applied, there's no extreme pressure. Gravity is the only pressure that's applied is due to gravity itself. And so those are two of the terms that we'll mess around with. The other one is not so easy for us to do. And if we take this inertial term, and if we go over to this term here, not a very straight line. And so this is an inertial term. This is viscous losses. The other expression that we've talked about in this class is the Reynolds number, after Osborne-Reynolds. And the Reynolds number is the ratio of inertial to viscous forces. So we're still recapping stuff from last week. So inertial forces to viscous forces. We don't really know what these viscous forces are. We know that the units of this have to be units of length, but we don't know what the other components are. But we do know what these components are. So one easier way for us to do that is to just go back to here. Let's look at this. Go back a few pages. More than a few. There, right there. Is this. So we're interested in figuring out exactly what the Reynolds number. We said that the Reynolds number is the ratio of inertia to viscous forces. The easiest way to figure out exactly what those are just to look at what these would be. So we know from inertia, the force that's due to inertia is F equals ma, mass times acceleration. Mass is equal to a volume times a density, by definition, right? So we don't care about what the, we care about the units, but not what the specific components are. A volume is units of length cubed. An acceleration is meters per second squared. So this is meters per second squared. So this is the product of a volume and an acceleration, right? These two. And so the units for this end up being, the units of this end up being density, length squared, and velocity squared. If we look at viscosity, the easiest way for us to define viscosity is we know that Newton's law of viscosity is a shear stress is equal to a viscosity multiplied by a change of velocity over a length. If we divide both sides through by some area, then this now is also a force, right? So if we have a force here and a force here, we can presumably divide those forces by each other. And so if we just take the units for this, this is viscosity, velocity divided by a length. Silly me, not divided by. I guess that's still right, but the force is actually a product, isn't it, of this? And so this is the area that's applied here. And so if we work through these, this is the term that ends up being the proportional to, it's actually a force per unit volume is really what it is. And so if we take these two terms and if we write rho L squared velocity squared divided by viscosity velocity length, then we have rho L V over mu. And that's exactly what Reynolds number has been. So without really going into much very sophisticated figuring out exactly what H sub L is, we now know that this other indexing parameter, just the ratio of the inertial term, v squared over 2g, to whatever the viscosity term is, which we've never really discussed in great detail. It's a bit kind of convoluted to figure, but we can figure it out definitely from Newton's law of viscosity. If we define these both as forces and divide two forces by each other, by definition a force over a force is a dimensionless term, and therefore we end up with Reynolds number. So this is the other important number we have. And so the final portion in maybe recapping exactly what we've talked about so far, maybe it's just before that, I'm going to use the figure that we have here, is this. And we'll use this in our study of flow in pipes. That to get any solution by this method of using similitude, so by running any experiments within a wind tunnel, sometimes a wind tunnel with buildings in it, sometimes a wind tunnel with bridges in it to look at the natural resonant frequencies of bridges like the Tacoma Narrows bridges, etc. Or to look at wind turbine blades, whatever you want, we have to satisfy these three requirements. The first is geometric similitude. In other words, the model that you want to look at, the length to height ratio of the model, if this is h, has to be the same as the length to height ratio of the prototype, not protocol. If it's not, then it's not really a true model of what you're dealing with. I guess that kind of makes sense. You know that when you make a scale model, 1 to 50 scale, that everything gets shrunk down by that same dimension, and it looks exactly the same as a model, but in a microcosm. So the first requirement is that the model that you have to deal with has to look like the true real system, and so that has to be shrunk in all dimensions the same. The second one is kinematic similitude, and that means that the flow patterns that you get around this have to be exactly the same. And so first of all, you have the same size. It satisfies geometric similitude because this prototype now and the model are in exact shrink down of each other, a scale replicate of each other. But now when it flows around it, you want the fact that you have eddies here and eddies here to occur in the same condition. And so in the model, that is satisfied if the Reynolds number of the model, which is a velocity, some characteristic length, and a density divided by viscosity, is equal to the Reynolds number for the prototype. It doesn't mean that all of these dimensions have to be the same, it just means that the combination of all those components have to be the same. And it says then that if this is met, then the flow regime you have past this will be identical. And so coming back to this pipe here, if we look at, well actually, or this model here for that matter, if we, how do I refresh that? I'm going to go back here. How do I well, I don't need to refresh it, I'll take it back there. So what this means is that the flow patterns that we have going over this wing, these are specific for a particular velocity and the viscosity of the fluid and density of the fluid, so it's air in this particular case by the looks of it. We could do this in water just as well, and so long as the Reynolds number was the same for this system in water or air, the form of these flow patterns around this wing would be identical. And so for that reason, then we could measure the forces that are applied to this and use those to calculate the real forces that are applied on the structure. Likewise, when we talk about this other case, go here, stall that out, and let me go back to this one, since it's relevant to what we're talking about here. Likewise, in this particular case, because we're talking about pipe flow, is that this flow is a laminar regime. There's no eddies that are going, it's going at a certain velocity. Now if we increase the velocity in this, the Reynolds number is changing, because Reynolds number is a linear function of velocity. So Reynolds number is changing, and now the flow regime is changing. So now we might expect that the forces that are applied on the side of this pipe, which we never really think about, because that's not really what we really want to figure out in pipe flow, would be changing because now the regime is changing. And so that's, I guess, what we're attempting to do. Maybe I'm overstating this. Whoops. Okay. So the final case, so geometric similitude has to look the same, shrink down to the model. Kinematic similitude is the flow regime has to be identical, and that's guaranteed if the Reynolds number is the same. The individual length scale probably isn't the same because it's a model, and you could also use different fluids if you wanted to with different densities and viscosities, but so long as you scale the velocity appropriately to match this prototype Reynolds number, you have a match. And the final one is we have dynamic similitude. And dynamic similitude often is saying that the Euler number of the model is, which we define as pressure divided by rho v squared, right? We just define this, is equal to the Euler number for the prototype. And so that's useful because now if we measure, for instance, the pressure that's applied on here, or if you take, say, the pressure that's applied on this face, and you multiply it by the pressure times the area of this face, that equals a force, right? Just as we said. So if you measure the force, or you could just measure directly the force that's applied to this block in trying to move it downstream, then we could also just write this as, what we could just write, we could multiply. So you could measure the force here in the model. If you know the density of the model, if you know the viscosity, sorry, the velocity that's flowing at, and you know the area of this face, then, because these are equivalent, this is equal to the force on the prototype divided by rho v squared a, prototype. So now you know the differences in the areas. If you're using the same velocity, well, you'll be using a different velocity, but you're using the same density of the fluid. Now you can calculate what the force is that's applied. So it's an incredibly powerful technique because now you could just shift through changing the velocities as you go across this, and you could map out exactly how the forces change as a function of velocity, and you have a relationship defined. And yeah, you probably remember that if when we use dimensional analysis, if we can define things in terms of, say, a Reynolds number and a Euler number, and it's always the same geometry, and we only have two pi terms that completely define our system, then all of a sudden we just have a relationship between those. That's really what we're doing. We're changing the velocity. If you increase the velocity, you calculate what the Euler number is in the model. You take the model, you increase the velocity, you calculate the force. You increase the velocity again, you calculate the force, and you've got this relationship. Now if you want to apply this relationship to this model, you just have to figure where on this line you are in terms of the Reynolds number that is the real world Reynolds number, and then you can figure out exactly what this point is, and then you know that the force that's going to be applied is this. That's it. So no equations needed, incredibly powerful technique, is used all the time because it deals with real fluids. It doesn't require that they be Newtonian fluids and satisfy Newton's law of linear law of velocity. Okay. So that's our recap, which perhaps took a bit longer than I wanted, but I think it's probably quite germane to what we're dealing with here. Okay. So what do we want to do now? We'll talk about pipe flows. So the last bit to tie this in, so we tie it in together, and it does relate to this idea of dimensionless analysis. What is a pipe flow, and how is it distinct from a storm sewer? And so it's important for us to realize that when we're talking about pipe flows, what makes a pipe flow is that the complete section of the pipe is filled with water. And if that's the case, then it's driven by an upstream pressure, which is larger than a downstream pressure, which drives a velocity as a result of this. If half the section of the pipe, or any fraction of the section, is filled with air, then it's no longer what we refer as a pipe flow. It would be what we'd refer to as an open channel flow. We can't now apply an upstream pressure here in the fluid and a downstream pressure in the fluid and sustain them, because it'll just short circuit through the air and we won't be able to sustain those pressures. So the only thing that will drive this flow in this open pipe, half section filled or 3/4 section filled pipe, is gravity. So if it's horizontal, it'll be stagnant. If it's inclined, then it will be flowing. But the only force that's making it flow is gravity, the change in gravity between upstream and downstream. And that's different from pipe flow. So that's the one thing that's different from us. And so we need to be able to account for that. And so our interest in looking at pipe flows is to account for what is this head loss. This will be one thing that we want to figure out. What is this HL that we have to apply to be able to solve Bernoulli's equation for pipes? How does it vary, for instance, with the fact that the walls of this pipe might not be absolutely smooth, but might have some roughness attached to them? And we'll define this roughness in terms of some parameter which we'll call epsilon as a function of the diameter of the pipe. And how, as a function of Reynolds number, which we know is a function of a velocity, a characteristic dimension that we can choose, and we'll choose that characteristic dimension to be the diameter of the pipe, a density of the fluid, and a viscosity of the fluid. How does this transition from laminar flow, where this little bead of dye that's going down the length of the pipe doesn't change? So this was in our YouTube video. This was the first case at low velocities. We upped the velocity, then all of a sudden there was a little jump and a wiggle in it, and if we kept on increasing the velocity, then it would get more of a wiggle. And we find out that this is indexed by this parameter of Reynolds number, which is this kinematic similitude parameter. To get the flow regime exactly the same, we have to have exactly the same Reynolds number. Not exactly the same velocity, but exactly the same Reynolds number. So that's kind of the big picture of where we're going. I'll make one other point before we kind of leave this, and I'm going to roll back to this just so I got a bit of place. So the big picture for what we're dealing with now for the next 6 weeks is we're going to talk about pipe flow. We're going to talk about external flows. And we're going to talk about open channel flows. And so with this territory, we can think of these as similar in some ways. If you think of pipe flow, then we're often interested in looking at what is the velocity that flows through this pipe as a function of a pressure gradient, which would be P1 minus P2, the upstream, right, over a length of pipe. And the flow is inside here. So you can imagine that since there's a change in pressure, P1 minus P2, and if we multiply that by the cross-sectional area of this pipe, that is equal to a force, right, by definition. And we never really think of this because we're interested in solving for pipes for what is the pressure, what is the flow rate that we can get if we apply a pressure on this upstream. But because there's a force that's applied for this, we're losing a force, a big force here, and there has to be a smaller force acting up here because it's a smaller pressure. To be able to hold this pipe in place, we have to apply a force to do that. We never really think about it. And the reason we have to apply this force is because there are shear stresses that are applied on the side of this pipe which are resisting this flow. So to be able to hold this pipe in place, we have to think about the force that would be applied. If you think about it, if we're looking at external flows, this is now a pipe that instead of stuff flowing through it, we're going to close off the end. If we close off the end, then the flow that goes down here has to go through a stagnation point around it and then out the other side, just like going around a wing, right? And maybe this is more apparent. There would be a different pressure here, upstream, a different pressure here, downstream. And again, we can get a force that we'd have to apply to this. And the force is going to be equal to what? It's going to be the difference in those pressures, P1 minus P2, whatever those pressures are, multiplied by the end area. So it's actually no different from this, right? It's exactly the same. And so if we think about it, external flows and internal flows, we could call this internal flows if we wanted to, I guess, are really the same. The only thing is that we're interested in something else. In internal flows, we typically want to know how much energy do we have to push to provide to be able to push stuff along the inside of the system at some given velocity. In external flows, we're typically interested in if we have flow past this at some velocity, what is the difference in pressures upstream and downstream so we can make it strong enough so that the water tower doesn't get blown over when it's sitting in a gale, which is really what's going on. And so we can apply these same things in terms of dimensionless homogeneity. What did we call them? We called it dimensional, similitude. We talked about kinematic similitude. And we talked about dynamic similitude. Oops. I don't know, what am I doing here? Dynamic. D-Y-N, similitude. So, we can talk about the pipe first. So the pipe, what are our dimensions? We have a length to diameter ratio. We could think of as two length ratios. We talked about before the idea that we had a roughness here that we thought might influence things. And so we could also look at a ratio between the roughness and the diameter. These are both two non-dimensional parameters. They're both ratios of lengths, and therefore they have to have 0 dimensions. And we could think of those as behavior defining the system. In this case, what's kinematic similitude? Kinematic similitude is Reynolds number. We've already said that is a velocity of flow, a characteristic dimension. We could choose epsilon, or we could choose length, but it turns out that the real important dimension here is actually the diameter of the pipe, which may be the same in each of these cases. What else? A density of the fluid divided by viscosity of the fluid flowing around it. So this is density of the fluid, viscosity of the fluid, not density of the object. I guess there is no object in this case. And so in terms of dynamic similitude, well, we talked about an Euler number being a pressure change divided by a density and the speed at which something goes. And so those are exactly the kinds of behaviors that we want to be able to characterize this. So if we wanted to apply dimensional similitude here, it again would be in terms of the scaling of this structure, a closed pipe in this case. It might be influenced by the roughness. And because for any of you who've looked ahead at some of the things we'll talk about, one of the reasons that a golf ball is dimpled is that when you hit it, it wants to make it flow turbulent early on, so that as you transfer to being a turbulent flow, instead of having this big viscous drag around the golf ball, you have this very thin boundary layer which really doesn't offer much resistance. So the sooner you get at any velocity into that boundary layer regime, it has less drag and therefore it goes further. So that's the reason that a golf ball has dimples in it, which you may or may not know. In terms of kinematic similitude, this is again Reynolds number, a velocity, a characteristic dimension, a density, and a viscosity. And again, the Euler number has a pressure divided by density and velocity squared. And so exactly the same terms apply in this. And it would do in open channel flows. I guess open channel flows would be something that would be half filled. And it's slightly different because now, again, we have the same dimensions that might characterize the dimensional similitude. Well, I'll just write them out just because I can. But we said that what's causing flow in this particular case is not so much the fact that we have a pressure applied between upstream and downstream, but gravity. And so, although we would look for kinematic similitude to be the same, so that the model that we would run to represent this would have the same Reynolds number, if we're looking at forces that are applied on this, and because the flows are driven only by gravity, not by an upstream pressure and a downstream pressure as they are in this case, then this Froude number would be the velocity of flow divided by gz, right? Any characteristic dimension, right? So this is a velocity. This should be gravitational acceleration, which is length over time squared times length. So it's length squared over time squared. Square root length squared over time squared is length over time. And so they cancel out because they're both velocities. And so when we index these behaviors, we use the Froude number to be able to do that. So in a big picture way of dealing with this, that's where we're going. This is weeks 10 and 11. Talk about pipe flows. This is week 12. I think your presentations are in week 13, and this is week 14. But they're all tied together by the same concepts, really. So they're not really different. So even though we're talking about internal flows, external flows, and open channel flows, it turns out that these variables, dimensional similitude, it looks the same in the model as it is in reality. Kinematic similitude, that the Reynolds number is the same, and therefore if Reynolds number is the same, then the dynamic similitude will take care of itself. Dynamic similitude is what we're after. So if you want to know what force you have to apply to be able to keep this water tower static, then we could just multiply this by an area on the top, an area on the bottom, and this is just a force divided by rho v squared a. And actually when we talk about this, we'll refer to this as a coefficient of drag. This is a dimensionless number. We've multiplied top and bottom by, say, the frontal area of this. And so this is the drag force that we have to apply to resist it being pushed downstream. It's a function of the density. If we double the density of the fluid at the same velocity, we'll have to apply twice the force. If we double the velocity, we have to apply 4 times the force, just from the scaling. And if we double the area, we'd have to double the force. If we double the diameter, we'd have to apply 4 times the force, right? Because the area would go up 4 times. So it's an incredibly powerful technique in terms of the scaling. We've solved no equations. We haven't solved any differential equations. But we've just realized that the fact that these 3 components, dimensional similitude, the flow regime looks the same because the Reynolds number is the same, allows us to be able to calculate what the forces are applied on the structure. So that makes perfect sense when we're talking about external flows, pardon me. It also applies when we're talking about internal flows, right? Because internal flows are no different. It's just that the drag on this between the pressure drop upstream and the smaller pressure downstream has to be resisted by something, and it's resisted by the viscosity of the flow on the walls of this pipe. And so when we're talking about pipe flows, we're also solving exactly for Euler number to be able to solve for our system. Okay. All right. So I probably went on more than I needed to, but well, that's fine. That's what I do, isn't it? Yeah, let's cut to the chase. So I was going to derive something, but let's not. Let's just use this. So this is the basic idea. So instead of deriving some equations by using Navier-Stokes equations, we could try and figure out exactly what the pipe flow equations were. So in other words, we want to figure out exactly what this equation is. Bernoulli plus the downstream component, whoops, I guess I could put in HP, is equal to Z2 plus P2 over gamma plus V2 squared over 2G plus HL. So we want to figure out exactly what this term is. We don't want to solve any differential equations. We realize we want to have viscosity in it, so that's why we have this term. We don't quite know what this term is going to mean, but that's why we have this term. We know we want to deal with not just laminar flow, but for all Reynolds numbers. And so perhaps doing some experiments at different flow rates would allow us to be able to characterize exactly what the behavior is. And we want to include the effects of a rough wall, because it makes a difference if it's a nice smooth steel pipe or if it's a concrete pipe, because they'd have different roughnesses. And we think in the same way that we talked about a golf ball being dimpled, perhaps the walls of an inside of a tube might make a difference if they're dimpled versus smooth. So what we could do is we could try and look at all the parameters which define our behavior. We've said what those parameters are already, right, in terms of this. It's a pressure change over a length. There's a diameter. There's a roughness here, which we'll call epsilon. We have a density of the fluid, and we have a viscosity of the fluid. And you could make the case that we should have gravity as well. So if I got everything here, we have a pressure drop that's driving flow. It's a function of a flow velocity, a diameter of the pipe, a length of the pipe, the roughness of the pipe, and the characteristics of the fluids. What do we know? We have 1, 2, 3, 4, 5, 6, 7 parameters. We have mass length, and time represented. So this is mass over length, right? Density. We have a velocity, which is length over time. So we have mass, length, and time all represented. So in other words, the dimensionless groups that we have would be 7 minus 3, which is equal to 4. So we could try guessing what those groups would be. If we go back to what we talked about before, actually, where is it? No, it wasn't there. I guess I was writing on here. If we go back to where we drew it here, this is it. Sorry. We talked about some dimensionless groups. We can guess them. We could do it formally using Buckingham pi, which you know how to use. But we could guess what those dimensionless groups would be. Let's guess that they might be these two, which are two dimensionless groups. Let's guess that it could be Reynolds number, which is another dimensionless group. And let's guess that it could be Euler number, which is a fourth dimensionless group. We said we needed 4. We're guessing that we could perhaps take those, and those would be good enough for us. So if we do this, we don't have to derive anything. This is the next page, I think, right? So we could write it exactly as this. Euler number is a function of Reynolds number, and this is a characteristic length dimension and a characteristic length dimension. Just don't need to call them anything really. But those are the numbers that define behavior. If we go back to Bernoulli, and if we look at the upstream flow, and we have a velocity 1 here and a velocity 2 here, and if the areas are the same, so if A1 equals A2, then by definition this and this are the same, right? They drop out. If it's on the same horizontal plane, then this and this drop out. If we're not pumping, then this drops out. And we're left with an equation which is P1 minus P2 over unit weight is equal to H sub L. This is what we want to figure out exactly is going on. We kind of have that, right? If you look at the bottom here, this here is upstream pressure minus downstream pressure. I guess if we wanted to, we could divide both sides by gamma W, in which case we'd have that, multiply both sides by half rho V squared, and we'd end up moving this. Bottom line is it turns out that if we manipulate this, we end up with this final expression here. The pressure drop as we go from upstream to downstream is this. If we divide it through by rho G, H is equal to pressure over rho G, right, by definition. So if I just take this and divide both sides by rho G, then we have this is equal to our head loss, which is a function of some factor, which is a function of Reynolds number and relative roughness. It's a function of the length of the pipe normalized with its diameter, and it's a function of these two terms, this velocity here and this velocity have cancelled out because it's the same cross-sectional area, but implicit in this term here is the fact that there's a term that's a function of the velocity squared term, the roughness term. And so this is the one term that we'll use in this class. It says that this head loss, which is what we want, is going to be a function of some parameter, the length of pipe divided by its diameter, and how quickly the flow is going. This has no units. This, as we'll find out, has no units. This has units of length. This has units of length. And so this is the term. So the only thing that we're going to need for this next 2 weeks is exactly an understanding of how to use Bernoulli's equation, which is this, that includes a term which might also include pumping, but certainly includes this loss term. And this loss term is very straightforwardly given by this expression here. It's a function of the velocity head and a function of the geometry of the pipe, length over diameter, and some friction factor. And what we'll find out is that this friction factor is a function of Reynolds number. And we'll use what are called Moody charts, which give relationships for laminar flow and then turbulent flow. Doesn't matter. You'll see these many times. Whoops. And it allows us to calculate what is friction factor from never ever having solved an equation, never having solved a differential equation, but just by doing experiments. So you go in the lab, you take a pipe, has a certain roughness, certain length, you measure the pressure drop along it, and you're able to figure out exactly what this friction factor is. You plot a point. You do another experiment at a higher velocity, you measure the friction factor, the pressure drop between 2 points. From the Euler parameter, you got another point. You do it again at a different velocity, and you have a relationship. That relationship applies to every single pipe that you'd use, at every single velocity that you use, so long as you take care of these three requirements. Dimensional similitude, kinematic similitude, which is code for the Reynolds number is the same, and dynamic similitude, which means that the Euler number is the same. And so hopefully you see that this is really an Euler number, this is a Reynolds number, this is a geometry, and this is a geometry, right? Those terms. So, sorry, went over. Too exciting, this stuff, isn't it? Okay, well, we'll continue next time. So, I'm happy to take questions if you have any, but if you want to scarper as well, that's good too. Okay? Thank you.